Hi, this talk is about almost optimal inapproximability of multidimensional packing problems. So I'll first start with defining what packing problems are. In these problems, there are n items. Each items have sizes a1 to an, which are real numbers in 0 to 1. The objective is to pack the items into bins effectively. So there are multiple ways to formulate the problem. So classical way is the so-called bin packing, where each bin has capacity 1, and the objective is to minimize the number of bins used. So here we have 5 items, and each bin has capacity 1. So we have 3 bins which are sufficient to pack these items. Uh, Another way to formulate this problem is multiprocessor scheduling, where you are given a fixed number of bins, and the objective is to minimize the maximum load on a particular bin, on like overall the bins. There's a dual version, relatively less studied problem called bin covering, where the objective is to maximize the number of bins, and each bin should get at least one load. This is the dual problem of bin packing. Okay, turns out that all these problems are NP-hard. So we are interested in approximation algorithms for the problem. And turns out all of them also have a polynomial time approximation scheme, where we can find 1 plus epsilon factor approximation running in time polynomial in n comma 1 over epsilon. And one small note is that these approximation algorithms for bin packing are asymptotic, where we study the setting when the optimal value is large, because distinguishing between the case that opt is 2 versus opt is 3 is also NP-hard. So we only study the setting when the opt is large enough. Okay, so this work is about multidimensional generalization of these problems, where each job is actually a vector in 0, 1 to the d. It's a d-dimensional vector. So the corresponding problems are vector bin packing, vector scheduling, and vector bin covering. So why are we interested in these problems? So first of all, they are quite fundamental problems in theory. They have been well studied for quite some time, and the techniques developed in studying these problems have also found applications elsewhere. And in practice, most of the scheduling problems are actually multidimensional. Oftentimes, there are multiple resources for each job, let's say CPU, memory, and so on. So coming back to the problems, I'll first define the 3 problems formally. So in the vector bin packing problem, you have n vectors, d-dimensional, v1 to vn. And the objective is to assign to minimum number of machines, such that in each machine, the sum has at most 1 in every coordinate. Note that we want the sum to be 1 in like every coordinate. So the L infinity norm of the sum has to be at most 1. So here you have, let's say, these 4 vectors. We can pack into these 3 bins, so that in each bin the sum has norm L infinity norm at most 1. Okay, and d equal to 1, it's the same as bin packing. And already when d equal to 2, we know that there is no p-task for the problem. So it's there is some constant such that it is hard to approximate within that constant. Okay. In the algorithm side, there's a of d factor approximation algorithm, which is like generalizing the p-task of bin packing. And when d is part of the input, where like the d can grow with n the number of items, this is actually tight. There's a simple d to the 1 minus epsilon hardness shown very long time back. What about the case when d is a fixed constant? So think of maybe like 10 or 100. So here, from like a theory perspective, the algorithms can run in time into the some function of d, like arbitrary function f. This is it's been a well studied setting for 2 reasons. One, in practice, d is oftentimes a constant, and 2, in theory, it turns out that this actually helps a lot. And we can get off Landy factor approximation algorithms, and they have been improved, slightly improved to Landy plus a constant as well. Um, on the hardness side, it's still that there is no petas is the one that we know. And the question is whether there is a constant factor approximation when D is fixed. Okay, which has been asked in multiple previous works. Okay, coming back to other multidimensional problems, vector scheduling is the generalization of multiprocessor scheduling. In this problem, you have n vectors v1 to vn and a number of machines m, fixed number of them. You have to assign the vectors to the machine such that we minimize the maximum L infinity norm of the load vectors. So load vectors is the sum of vectors assigned to a particular machine. So here if we have 4 vectors and we assign these the 2 to each machine, and the L infinity norm of this vector is 1 and this is 1.1. So the make span of this scheduling is 1.1 and our objective is to minimize this maximum norm, L infinity norm. So D equal to 1, it's the same as multiprocess scheduling. Turns out for fixed D, you can actually get a p-test for the problem. And when D is part of the input, we know log D or log D approximation algorithm. On the hardness side, we know that there is no constant factor approximation shown by Chekuri and Khanna. And so the objective, like the goal here is to either obtain a hardness that grows with D or get better algorithmic results. Okay, finally, in the vector bin covering problem, it's the dual of vector bin packing where you have n vectors v1 to vn. Objective is to partition them into maximum number of parts such that in each part, the sum is at least 1 in every quad. So note that here we are not saying the sum is 1 in L infinity now. Here we are saying that the sum is 1 in every quad. And when D equal to 1, it's the same as bin covering. And generally, there is a log D factor approximation algorithm shown by Alan and others a long time back. And hardness, we know that it's APX hard when D is equal to 2. Ray has shown recently this result. And the question is to obtain hardness that goes with D. So these are the status of the 3 problems. And now I'll state our results. So first for vector bin packing, when D equal to, when D is the fixed, which is the interesting case, we show that it is hard to approximate within omega of log D factor. Recall that there is a log D plus of 1 factor approximation algorithm in this set. For vector scheduling, where there is a log D or pi log D approximation algorithm, when D is part of the input, we show log D to the 1 minus epsilon factor hardness. Okay, and for vector bin covering, we show omega of log D over log D hardness when D is again grows with the input. So for bin packing and bin covering, our hardness is assuming P not equal to NP. For vector scheduling, we need the assumption that NP has no quasi-polynomial time algorithms. So we summarize our results in this table. So for vector bin packing, our results is for the fixed D case, we show omega of log D hardness. And for vector scheduling arbitrary D case, we show log D to the 1 minus epsilon. And for bin covering, we get almost tight hardness as well. So now in the rest of the time, I outline the proof of vector bin packing hardness. Okay, so recall the problem first. In this problem, the input is n vectors v1 to vn. And the objective is to partition them into minimum number of parts such that in each part, the sum of the vectors is at most 1 in every coordinate. Okay, so we define this notion of a configuration where a subset I1 to Ik of 1 to n, the input has n vectors. So we say it's a configuration if the vectors corresponding to these indices has some L infinity norm at most 1. So it means that these vectors, you can pack them into a bin because the sum has L infinity norm at most 1. So now if once with this definition, the problem is to divide the input into minimum number of configurations. Or if, you can also ask equivalently, you can say that the objective is to use minimum number of configurations to cover all the n elements 1 to n. Okay, so this problem where you are given n elements and a bunch of sets, and the objective is to cover each element using minimum number of sets. This is known as set cover. It's a very well studied problem. And I've just outlined a reduction from vector bin packing to set cover. So of course, there are some caveats here. First of all, these configurations, there could be exponential number of them. So computing them itself takes a lot of time. So how there's no way to do it, right? However, we can write the set cover LP, solve it, find the important configurations that get non-zero LP, and then proceed. The algorithms can proceed from there. This is actually how the algorithmic results are obtained. However, for our results, we are interested in showing hardness. So, so the idea is to think in reverse terms. So we want to start with the set cover instance and come up with the vector bin packing instance. Okay. So more formally, I can ask this question as which set cover instances can be formulated as d-dimensional vector bin packing instance. Okay. So in particular, suppose that we are given a set family F. Can we find some n vectors v1 to vn, d-dimensional vectors, such that the configurations of this bin packing instance, vector bin packing instance, are exactly the sets in the family? In other words, a set S is in the family and only if the sum of the vectors corresponding to indices has L infinitum at most. If this is true, then the family F is the family of configurations. So with this in mind, we define this packing dimension of a set families, which is that it's the smallest integer d, such that there are these vectors v1 to vn, d-dimensional vectors, such that their sum has L infinitum at most 1, and only if S is in the family. In other words, we have to find these vectors such that the sets that are allowed are already given to you. Only these sets, the indices corresponding to these sets, should have some L infinitum at most 1. And if the a priori it's not clear such a D even exists. So if no such D exists, we say that the packing dimension is infinite. Okay. First of all, there are two conditions which are needed for packing dimension to be finite. First, the set family has to be downward closed. That is, if a set S is in the family, any subset of S should also be in the family. This is because if sum of vectors has L infinitum at most 1, any subset also has some L infinitum at most 1. And second, there shouldn't be any isolated elements. This is more like a technical detail because I'm requiring the vectors to be in 0, 1 to the d. So any single vector has L infinitum at most 1. So there shouldn't be any isolated elements. That is, every single element has to be part of a set. Okay. It turns out that these two conditions are sufficient. So not too hard to prove this, but we won't go over it. This is a quick example of a set family. Here you have 6 sets, and we can just find a one-dimensional embedding for the set system. Like this set system has packing dimension at most 1. We can also clearly see that this is downward closed and has no isolated elements as well. Okay, so coming back to our hardness, we can note that if a packing dimension of a family is at most d, the set cover problem is a d-dimensional vector bin packing problem. Okay. Of course, there is one other thing that I'm hiding, which is that you need to be able to find these vectors efficiently as well. Turns out that for all the results that we have, that is the case. There are no settings where we know that there exist the vectors, but we can't find. Every proof is constructive here. Okay, so to summarize, the main idea behind the hardness is this notion of packing dimension, where you want to show that there is this set family F, which is set cover is hard to approximate on these set families, and the set family has packing dimension at most D. If that is the case, then you can automatically get that vector bin packing is hard to approximate within F of D. And the idea is that set cover is a very well studied problem, so we should be able to find the hard instances. However, there are some roadblocks. So first of all, set cover, there is omega of ln and hardness, which is the standard FOCS hardness. But it turns out that packing dimension for these instances actually grows with time, which we cannot afford as we are operating in the constant D regime. So we need that the packing dimension of set families that we are interested to be a constant. So are there more structured set systems which have this property? So they should have small packing dimension, but the set cover is also hard on them. And turns out that the answer is yes. We get this both properties that we need in this simple bounded set families. So what are the simple bounded set families? Simple indicates that every two sets intersect in at most one element. These are also known as linear set families. They have been well studied more in combinatorics rather than algorithmic results per se, but still there have been many results on that. The bounded is just each set has bounded size, and each element also appears in a bounded number of them. Okay, so turns out that set cover is hard on simple bounded set families. In particular, you can get omega of ln k factor approximation hardness on simple k delta bounded set families when delta is polynomial. So I need one thing to note is that this omega of ln k is tight, because set cover on set systems where each set has size at most k has a of ln k approximation algorithm. And this is actually not that hard to prove, this result. It follows almost immediately from set cover hardness on simple set systems, which has been shown by Kumar, Arya, and Ramesh. After from their result, it's just a modification of parameters. So the other part is to show that simple bounded set families have bounded packing dimension, or constant packing dimension. In particular, simple k delta bounded set family without no isolated elements has packing dimension polynomial in k and delta. And finally, this downward closure is because we need to add all subsets of sets that we are studying as well, because we need for packing dimension to be finite, we need that property. So this is our main technical result. It's fairly intense. So we study specific set systems called sunflower bouquets and obtain embeddings for them, and then use these embeddings repeatedly to obtain embeddings for arbitrary set families. So this two together completes the proof. To summarize, the idea is to come up with a notion of packing dimension for set families, and then if set families have small packing dimension, we can use set cover on these instances as we can reduce it to vector bin packing instances, and then we use the simple bounded set families which have both the properties that we need. So to summarize, we in this work we get hardness of multidimensional packing problems, vector bin packing, vector scheduling, and bin covering. There are many open problems, including more applications of packing dimension. For example, can we use it to get geometric bin packing, or can we use the idea of packing dimension to get better hardness or two-dimensional bin packing, and so on. Thank you.